Okay. First of all, I want to show you that it is possible to see the pictures I tried to draw. Actually, they make sense if I don't draw them by hand. So I will go very fast through what was supposed to be the presentation. So this is a polyhedron, the intersection of finitely many half spaces, and if it is bounded, it is a polytope, right? And this is how a cone would look, which was the intersection of finitely many half spaces. And if the generators are linearly independent, then we have a simplicial cone. Remember, unimodular versus non-unimodular, depending on how many lattice points we have in the fundamental parallelepiped, which is the half-open area defined by the generators. And this was a supporting hyperplane is a hyperplane that touches the polytope or polyhedron but doesn't cut it in two. And the intersection of a supporting hyperplane with our polyhedron defines a face. If it's zero-dimensional, it's a vertex. If it's one-dimensional, it's an edge. Otherwise, so if it is a d-1 dimensional face of a d-dimensional polytope, then it's a facet. And this was the vertex cones. So it's the smallest cone containing the polyhedron and having the apex at the vertex. And here is, you remember that, right? So computing the lattice points in the semigroup defined by 1, 0, 1, 3. And this is how we're gathering stuff. And this is here, now it is quite obvious that this has this rational function version. And if we move, we just add 1 in the exponents here. And we pull out a z1, z2, which appears in the numerator. And there you go. This is the lattice points in the fundamental parallelepiped. And that's the lemma we used throughout this week. The numerator is the numerator enumerates the lattice points in the fundamental parallelepiped, and the denominator is the product of 1 minus z to the generators. And that holds for any simplicial cone, any dimension, etc. And this was about flipping rays. The example was 1 over 1 minus z, the natural numbers. And if we pull out a minus z in the denominator, we take it upstairs, and then we get the flipped ray, which if we add them, we get 0 at the level of rational generating functions. And here's the Brion's theorem, the example I tried to do with the pentagon. We want the generating function for the lattice points in this pentagon, and we said we take the space, the plane, and we remove these blue cones, and I will take each one of them and I will just flip one ray, which means I will change the openness, the direction, and the sign, and I will do this for all 5. Here's the example. So for this polytope has 4 vertex cones, 1, 2, 3, and 4, right? And the corresponding 4 rational generating functions are these. I can tell you that this one is for that one, because the generators are 1, 0, 0, 1. And let's find this one. That's also quite easy to find. It's that, because the apex is shifted by 3, 4. And the generators are minus 1, minus 1, which is this one, and 1, minus 2, which is that, right? And if you actually do this computation, you end up with this polynomial, which is exactly the lattice points. So obviously the rational generating function of a bounded thing is a polynomial, right? Because it has finitely many lattice points inside. That's an example of a Brion decomposition of this polytope. Okay. And yeah, this we saw about the intersections, that the upper one doesn't work, the lower one works, right? And here, if we take the decomposition we had in the previous example, and we make all cones look forward, look in this direction, we get what we call a Lorentz-Barcenco decomposition. For example, this cone here, this is looking that direction, so we will flip it. It is this generator now. So if we flip it, we have to change the sign. It became a minus. We change the openness, and yeah, we flipped the direction. So that's the kind of decomposition we want, because now we can actually take intersections. We can cut, which was the second step in polyhedral omega, right? Okay. This is McMahon. Thankfully, I didn't try to draw that one on the board. And this I did try to write. This is the definition of the omega operator. And this was the example. Here is a nice, we have the 3 by 3 magic squares. And it is defined by these equations, right? So this is the full generating function. We have 6 variables since it's symmetric magic squares. This is the crude generating function. We put the equations as exponents. And then if we apply omega equals, what we get is this one. And if we put all zi equal to 1, we get the counting generating function, which is this Q thing. I use Q, right? So this is a counting generating function for the 3 by 3 symmetric magic squares. And here's a bit of history. So we start with McMahon, who did employ Elliot. Then in the 70s, Stanley actually kind of saw the work of McMahon, but I don't think that it continued a lot in this direction. Late 90s, early 2000s, Anders and Paule started this partition analysis series, from which we have 2 packages, omega and omega 2, which are different partial fraction decompositions. Then Nesin also has a series of different partial fraction decompositions and different methods for that. Thomas, in her PhD, uses actually McMahon and Elliot, introduce a more constrained programming approach to the problem. And this is what we discussed, which is inspired by Elliot and essentially omega 2. And polyhedral geometry, right? Which is not in the picture of partition analysis until that point. Okay, I will skip that. Or I will show you this, how this works, this bisection method of Elliot. This is the geometry of Elliot's partial fraction decomposition. So that's how we do it, right? We start cutting in the middle, and we stop when we are above the xy plane. And this was McMahon's rule. Please don't tell me these are more visible than what I drew on the board. So here's again the intersection, the projection, and the lattice points in the fundamental parallelepiped. You see this segment that was giving us this finite geometric series. This is the second polynomial I didn't dare to write on the board about the Andrews-Paule-Riese decomposition. And so this is what we have, and that's the decomposition we get. So we have a fat cone, and we cut it into, so this is that minus this one. And you see here is half open, because that's, this is open, because that comes from the polynomials they have in the recursive partial fraction decomposition. And here is the lift we did, right, in the extra dimension. You remember this inequality? Yeah, it is indeed my favorite. And then we found the intersection, and we kept only things above, and then there are these lattice points in there, which we can project and get the polyhedron containing the solutions to our system. Okay. I just want to show you this one, because this I really failed to draw. So we had this cone, and then we cut with a hyperplane, and we keep only the things above, right? Now, this means we want this polyhedron, and the Brion decomposition of that consists of these 2 cones. And in order to find, so V1 was part of the input. I'm showing here. V1 was part of the input. W1 is easy to compute, and G1 lies exactly as Kant said in the intersection of V1 and V3. And this is how we're computing all of them. Good. Okay, now, are there questions? So essentially what the polyhedral omega is doing is, instead of, this would be the polyhedral geometric approach. We first enumerate all vertices, all edge direction, we triangulate our cones, and we compute rational functions. And the partition analysis approach is to do the McMahon lifting and then evaluate the operator using analytic rules. But what we do here is instead of doing the complicated polyhedral part, we just do McMahon lifting. And instead of doing the analytic evaluation, we use the geometric decomposition. But that's all nice. But what's even better is to see it working, hopefully. Okay.
It's too little for us to see.
It's a good point. Yeah. No.
Just hit the big A, so the font becomes larger.
Where is it?
Go up, left, right, right. The big A, yes.
Wow. See, technology works. Thank you. So, okay. Let's close this warning. Yeah, so here we just import polyhedral omega. These are the files needed. And I have a function. This is just for the demo. We give matrix A, vector B, whether we have equations or inequalities. And the rest just is for reporting that I want to see every step of the algorithm. So I first do the decomposition to get my cones, and then I compute the fundamental parallelepipeds, and then I write down the rational functions. Okay? That's what this does. And let's see now the example that I couldn't do on the board yesterday. So what was the inequality? It was 2, 3. 2x plus 3 greater or equal 5, right? So why is it taking so long? So yeah, doing the decomposition, it took not much. So is it milliseconds? Yeah. And we found 2 cones, as we expected. Until there, we were correct. So here are the 2 cones. The generators are 0, 1, and 3 minus 2. And the apex is 0, 5 over 3. This is, yesterday, it's a rational vertex. So the way the point it cuts is rational. And this is a closed cone. And the second cone has the same generators, and the apex is 5 over 2, 0. And the second facet is open. Why is that? Because actually I did flip in order to make, the generators were like this, and I flipped them so that they look in the same direction. So you see it's the same here, and this is why I get a -1 for the second cone. I have to change the sign, the direction, and the openness. And this is the generating function. No, that's actually an expansion of it. Before expanding it, I still have to print it. SR is the symbolic ring. So this is the rational generating function of the solutions in there. And that's Z1, Z2, right? I get all pairs. And if I want, I can take the Taylor expansion of the first terms and get the exponents will be the solutions here. Like 2 is a solution. 0, 2 is the first solution, 1, 1 is the solution, etc. Okay, questions until here? Okay, partitions in distinct parts. How do we do that? We discussed it, right? Okay, so xi has to be strictly equal than xi plus 1, which also means xi minus xi plus 1 is greater or equal than 1, right? And I mean, we can encode strict inequalities, but we don't need here. So what we need is the following matrix. It's 1 minus 1, 0, 0, 1 minus 1, etc., right? And all ones here. Okay. This is what this line here does. So if I is equal to j, we get minus 1. If I and j are 1 off, we put 1. Otherwise, we put minus 1, and everywhere else we put. Otherwise, if I is equal to j, we put minus 1, and everywhere else we put 0, and we get a vector of b's with all 1s. Let's do that. Let's do it for 5, n equals 5. This is for 5 parts, right? Yeah. So that will be the matrix, and it takes no time to compute everything. But what I want to do afterwards is I have my z variables, but I want to put q. So I will substitute every variable by q. This is evaluation. This star before a list, it unpacks the list in Python. So I will evaluate this RR, which was my rational function, with a q everywhere. And what I get is, where is it? So these are the cones I got. Right. I'm printing it now. It's this one. So this is the generating function for distinct partitions at 5 parts. I can do 10. I mean, I can do any n, right? So it makes no difference, really. You see this Q45, this is the first. Okay, let's discuss this a bit. The denominator is, I mean, you know this better than I do, right? You can see what this is. We can see this in the generators, right? If you see these generators, we have something. Okay, what is the difference here? In the generators, I can really see with this q to the 6, where are these 6 coming from, right? It's all ones in different variables, which for this particular case, it's easy. We know, we can understand how distinct parts work, right? And this Q45 is the shift where we start from. And that would be, yeah, that's to be expected. But we can also see RR. This one? Yeah. So this is actually the generating function, the multivariate generating function, okay? So how do we get this 45? It comes from there. And as you see, so this is how we get also the denominator. Questions? Requests? Yeah, okay. This is, if we take the, yeah, that's, wow. Something, I changed something here, I think. Right, yeah, no, I wanted to just say, what is the difference, if I want part parts with the difference 2, I just change this thing here, right? I change the right hand side, and now I have partitions with parts that have difference 2. I'm sorry I'm going up and down, but yeah, so I made it a bit smaller. And that would be now the Q and the full generating functions for that.
Why not shoot for the square?
Q?
Look at the numerator. We expected a square because difference 2 is right in the margin, right? So we want a square of that.
Where is it? Right margin 2, so 16 plus 4?
This is in up to 5 parts. Okay. Where do you want the square? Here. So the question is, why do I get 20 instead of square? No, it's not, because actually I don't allow repetition here. So then if I have 5 non-zero parts, what is it?
Do you allow zeros?
No.
So we start at
Well, I allow up to 1 0, right?
You can allow 1 0.
I think so.
Yeah, okay, it makes sense. Okay.
So it is exactly, so let's say the inequalities. Let's say that the last one can be 0, but the others cannot be.
Okay.
Yeah, actually this is the exactly what we discussed, exactly the Rogers-Amanujan. This is from 4 years ago, the code we had to analyze the generators of the cones. Because somebody asked how we get the generators. I mean, there are geometric methods for that. That's easy. And in Sage is just like you ask the raise, done. And then you see all the structure that you would expect. So the thing is, you may get a lot of cones in the decomposition, depending on your on the problem you decide to see. But as I said, actually, usually here you will see a lot of structure. Well, not if you look at these thousands of cones, but for example, if we go in the first example, where is it? So here, for example, that was the difference 2. We actually get only 2 cones, right? And they even have the same generators. No, sorry, they cannot have the same generators because they have the same apex, okay? And they have the same openness, and they have the same sign, which means that this is a cone that you decomposed into 2 cones, okay? And then you may ask questions about what is one cone and what is the other. Also, that's people like to see apparently products into sums. So that's a sum of cones, right? So that's a sum of rational functions. Every cone is a rational function. You get a bunch of cones, that's a sum of rational functions. Yeah, I'm going to make it. So, well, actually, do you have questions? Okay, so this is how we do the congruence part. That's another class I want to discuss. Halume asked the other day about up to 2 repetitions. This we can also do as linear, right? Because this just means what? Smaller or equal or something? Strictly, right? Yeah. So that's the condition. That we don't have three consecutive parts, three repetitions of the same part. So that's a linear version of it. Okay? Now, if my part is A or B mod M, what we can do is that X is, well, I shouldn't use this. So it's Km plus, how do we do this? Will I have to check my notes?
Km plus A or B.
Sorry?
Km plus A or B.
Plus A?
Or B.
Well, yeah. So, but A or B, so let's introduce 1 minus L. And this means, so, and multiply B with that, right? So L is either 0 or 1. If L is 1, then this is, if L is 1, then this is Km plus A. If L is 0,
AL.
sorry?
You put AL, so if L is 0, then you put B, L is 1, you put
So we need to get A minus B, right?
But
Okay.
AL plus L minus 1 times B.
Sorry, AL?
A times L plus L minus 1 times B.
Here?
No, 2. A times L. And then plus. Now L minus 1 times B.
Yeah, right.
1 minus L times B.
1 minus L.
So, and we want this to be, now, this is our, right, okay, this is, what I was trying to do is I pull out the L so that it's, I write as a variable, right? So, and we substituted one variable with two variables, right? Out of which one is non-negative as it used to be, and the other is a 0, 1 variable. And that's fine. So what happens is that now we described our, so partitions used to be cones usually, right? Most of them are, you have a cone with all the partitions. Now what you have is a cube in half of the dimensions, and the cone in the other dimensions, and every lattice point that is a solution, every partition is a point in the cube together with some point from the cone, right? In the half of the dimensions are in the cube, half of them are in the cone. So that's a lattice point that corresponds to one of your partitions. And so that's what we do here. Actually, let me expand this, as I said, to convince you. Psi is 5 Ki plus, what is this now? 1, it's Li plus 1 minus Li 4 minus 3 Li plus 4, right? Which means that if we have the inequality in our partitions now, xi greater or equal than xi minus 1, xi plus 1, we get a 5 here and a 5 there, a 5 here and a 3, sorry, a 5 here and a 3 there, a 5 here and a 3 there, because these variables now are going together, right? And where is my right hand side? Yes, I want it to be greater or equal. The 4s are cancelling, the constants are cancelling in the subtraction, and then I want the I also introduced these inequalities which tell me that these LIs, they're all smaller or equal than 1. So this together with that, they tell me that the corresponding LI is smaller or equal than 1. Here we could see it better, right? And let's run it. So we computed some cones. So we found 9 cones. As you see, I didn't ask you to see it earlier, but all the bottleneck of the computation is always the parallelepiped computation. That's what takes the longest. And here we have our variables. And let me, so what we do is substitute again. What I want is this substitution. No, apparently that's not the substitution I wanted. And am I getting does this function look like anything to you? Like this is the denominator.
Can you indicate where the equality is?
Sorry?
No equality, that's the all rational function.
Yeah. For up to 5 parts. So, yeah, I know that you like infinite stuff, but here we still find it.
The denominator is a little true factor for our tastes.
Okay, we can do that.
I mean, in the previous example, we had the nice true factorial, right? We don't have it anymore.
No, because we have here.
There you have to work it out.
Here probably, so we factored it too much, right? You're right. Anyway, I believe this is the generating function, the Q1. The Z1 is probably a bit bigger. Let me print it here. If we see the Z1 though, the full one, you can see where things come from. Well, when I say you can see, it may be exaggeration in terms of really seeing it, but you have control of what happens. And this is when I said that a lot of cancellations happen, this is what I meant, right? This function turns into that. Anyway.
And it's not the whole thing.
Sorry?
It's not the whole thing.
No, yeah, of course. If you want to see all of it, you have to do it on your own time. So, okay. Now, it's just something about current research, because this algorithm is already 10 years old, and the one problem I have with this is that the dimension has to be fixed. And I know that for partition problems, this doesn't really make sense. So we want to let n, so n is not fixed. I don't want to say it goes to infinity, but it's not fixed. Why I'm saying this? Because actually we want formulas where n is present. It's not really infinity. We count with respect to n, but n is a parameter, right? Okay, and this is the symbolic version of that, where we can do all the geometry I presented in dimension when the dimension is part of the input, like n in dimension d. We use d for dimension, and you can do everything, and in the end you would get a generating function. So the product would be from 1 to d. Okay? And for this we need a bit of rewriting techniques, or I don't know, this is the approach we have at least. But we're not quite there. I'm sure 4 years from now, in the next meeting. Well, I'm not sure, but I hope it will be ready. Because I'm pretty sure 4 years ago, I was sure that it would be ready today. But yeah, it's a nice topic. I have also applied for a project, let's see. It combines a bit of computer science with this stuff, with nice geometry and nice number theory. So, and if it works, a lot of whatever we discussed this week can be automated.
So one thing I want to add is those Q rational functions, those Q series are polynomial or recurrent, as if you like, and they're known series. The recurrence fits what you say the polynomials, which also shows up in things. So the congruent condition side, with number of parts bounded, is somehow fits the literature, although we couldn't work it to go to the other side.
You mean from the last time we discussed that, right? Yeah. Yeah. Questions? Okay. I mean, my point is just do not give up on geometry and try to see things in. So what I learned these years is that going in higher dimension, going high is good. So you see things more clearly. Things like going to the multivariate, and by multivariate I mean that one, because people usually say we should go multivariate, and they mean introduce an extra variable. That's not going to cut it. So you have to, if you go there, you really see things, because, or you can do all the kinds of different substitutions there. And playing around with these things actually gives you a lot of intuition about your objects, which are, again, partitions are solutions to linear definite systems, right? So the fact that we like them in a different way doesn't mean that it's not that. It is. So we can use the tools to analyze them that people developed for solving linear definite systems, like McMahon, who nobody can say was not doing partitions. Okay, done.